Okay, so let's look at ions. We're going to look at the electron configurations, magnetic properties, ionic radii, and ionization energies. Lots of topics for one section. So anions form when an atom gains electrons. That's why it has a negative charge. And so then if we're looking at the electron configuration of the ion, we have to add electrons to the electron configuration. That usually doesn't cause too much trouble. A cation forms when an electron loses. When an atom loses electrons. Electrons can't lose atoms. Cations form when the atom loses electrons. Those electrons are going to be lost from the valence shell, and then we subtract electrons. So for the main group elements, you just remove the electrons from the end. Reverse order of filling. So here the example is aluminum. Here's the electron configuration for aluminum. And when we make that into an ion, it's going to lose 3 electrons. And so we're going to lose this 3p1 electron and these 2 electrons here. Both of those go away. If we're looking at the orbital diagram, there's 3s and 3p. And there were 2 electrons in here and 1 in here. When we make the ion, we take away 3 electrons. How do we know it's 3? Because there's a +3 charge. So that means we have to get rid of 3 electrons. So I'm going to get rid of this one and this one and this one. I'm just going to go from the end, reverse order of filling. So this one's gone and that one and this one. And so we end up with this electron configuration, which is the same as which noble gas? Neon, right? This is got the 2s and 2p sublevels full. So at the end of row 2 on the periodic table is neon. How many electrons does an aluminum 3+ ion have? Well, you kind of have to start with how many electrons does aluminum atom have? Its element number is kind of covered up by the tape, but you can figure it out because 14 is next to it, right? It's got 13 electrons as an atom. And then it loses 3. Now it's got 10 electrons, same number of electrons as neon, right? Which is why it loses 3, because this is a cool electron configuration, and aluminum feels better about himself when he looks like that. What about the transition metals? Well, they just have to be a little different, don't they? With the transition metals, we're going to remove the valence electrons first. And if we run out of electrons, we still need to remove more. Then we'll go into the core electrons. So we remove the valence electrons first, even if it does not correspond to reverse order of filling. So for an iron atom, here is its electron configuration. Where are the valence electrons? What's the highest level? 4. So the valence electrons are right here. Yeah? 2 valence electrons. So if we're going to lose 3 electrons, the valence electrons get lost first. So what it's doing here, from this one to this one, we're losing the 2 valence electrons. That's the 4s2 part. So let's go down here. I'm going to fill this in and make it an atom first. So get rid of that charge. That would be the orbital diagram for the iron atom. You see that? So I have 4s2 and I have 3d6. So there's 4s2 and 3d6. So we lose the valence electrons first. So these are valence electrons. Maybe I'll make it yellow. Those are the valence electrons. And so I'm going to lose those guys first. So we could take those away. Those are gone. And we've got a charge now. Well, I guess I could have just written it next to it. 2+, right? Because we lost 2 electrons. We need to lose 1 more electron. Now we're down into what were the core electrons, and so we can just take from the end. So from this 3d6, we need to lose 1 more electron. We're going to lose 1 of those, and that's this guy right here. So we're going to get rid of him. Oops, that's not what I meant to do. Like that. And now we've got our 3+ charge. So going from here to here, we lose a 3d electron. And I will try to trick you with this on an exam. I'll ask you something like what's the electron configuration of chromium or something? The chromium ion. And for the transition metals, you have to lose the valence electrons first, even if it's not reverse order of filling. The main group metals also lose valence electrons. So it's not like that's really an exception. What messes us up here is that when we talk about creating this electron configuration, we talk about adding those 3d electrons last. And so we kind of think, well, last in, first out. That's not how it is. Yeah, I guess in the hotel, when you're evacuating because of a fire, the people on the top floor get into the elevator first. Well, you shouldn't take the elevator. They should go down the stairs. But the people on the top floor are going to get out first. And so if we think about the hotel here, there are 2 electrons staying on the 4th floor of the hotel. And then we've got, 14 electrons? 6 plus 6 is 2, 14 electrons on the 3rd level, right? On the 3rd floor. So we're going to evacuate the people on the highest level first, so those 2 electrons go bye-bye, and then we'll start taking people out of the 3rd floor. I made that one up just now. You like it? Evacuating? I got a couple nods. We'll be good with that. Okay, magnetic properties. So some things are magnetic and some things aren't, right? You ever tried to stick a magnet to a piece of aluminum? Doesn't work, does it? So this thing over here, this plastic beaker, got magnets that we took out of those out of a hard drive. They're really strong. And so it sticks to the door jamb there because that's stainless steel, probably iron of some sort, and that's magnetic. This chalkboard tray, metal, doesn't stick because it's aluminum. Aluminum doesn't care about magnetic fields. Why? Has to do with paired and unpaired electrons. So an atom or an ion is paramagnetic if it has unpaired electrons, and it's diamagnetic if, I'm sorry, I got thinking about something else. So paramagnetic means that it's attracted to a magnetic field, and that's if it has unpaired electrons. That unpaired electron generates a magnetic field due to its spin, and that's what gets attracted to the magnetic field. Diamagnetic atoms or ions have electron configurations where everything's paired up, and those are slightly repelled by a magnetic field. So I have had a lot of trouble keeping these straight. So this is another case where we've got a pair, we have two pairs, and we have to get them matched up correctly. So we have paramagnetic, we have diamagnetic, we have attracted, did I spell that right? And repelled. Actually, we can just think of it as not attracted, slightly repelled. What my brain wants to do is paramagnetic somehow says it is magnetic to me. Oh wait, that is, never mind. Okay, back up a minute. That's what I have trained my mind to think. Para sounds like pair, right? P-A-I-R, two. And so paramagnetic, I think pair of electrons. And so that would mean it's not attracted to a magnetic field. But then we also have diamagnetic. And what does di mean? Two. So diamagnetic, 2 by 2, like Noah's Ark. All the electrons are paired up, they're marching along 2 by 2. Diamagnetic, 2 by 2, not attracted to a magnetic field. Paramagnetic is the other one, it is attracted. It's the unpaired electrons. When you have paired electrons, their spins are paired with each other, and so they're not really causing any magnetic fields of any kind. When you have a spinning electric field, it interacts with a magnetic field. Yes?
So if you put two paramagnetic things together, would be diamagnetic?
That's a good question. If you put two paramagnetic things together, would it be diamagnetic? No, because putting two paramagnetic things together does not mean merging their electrons necessarily. Right? So they could still have unpaired electrons. So it's a little more complicated than that. So this is a possible test question. Write the electron configuration and orbital diagram for each ion. Predict whether each will be paramagnetic or diamagnetic. So cobalt 2+. I like starting with the orbital diagram first. And so here it's entirely appropriate to use the noble gas shorthand, and so we've got argon. And then past argon, we're going to get into 4s. And then the next level is 3d. There's 3d, and this is 4s. And then on the periodic table, I can just count over. Well, I've got potassium and calcium. Those are the two electrons that are filling up this S room. And then 1, 2, 3, 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6, 7. That's cobalt. Okay? Everybody okay with that?
And that's as a noble gas configuration.
That's showing the noble gas configuration. Yeah. Because the core electrons are always going to be paired because it's full. It's just the valence things after the noble gas that could be unpaired. But we're not asked about cobalt 2+. I mean, we're not asked about the atom. We are asked about cobalt 2+. Just shoot me. So 2+ means I have to remove 2 electrons. And which ones I remove changes the answer. Because As it stands here, is this paramagnetic or diamagnetic? Are all the electrons paired up 2 by 2? No, it's not diamagnetic, it's paramagnetic. Okay, I have to remove 2 electrons. This is a transition element, right? It's tempting to remove 2 electrons here. We don't want to do that. We want to remove the valence electrons. Right, so we're going to take those out. So, is it paramagnetic or diamagnetic? It's paramagnetic. That's an excellent point. What if an atom has an odd number of electrons? Wouldn't it have to have at least one unpaired electron? Yes, it would. Mm-hmm. Yeah, if there's an ion, then you have to adjust the number of electrons. Yes. So it did tell us to write the electron configuration, so we probably should do that. Writing the electron configuration would be AR. The atom would be 4s2, 3d7. And then when we make the ion, we get rid of the 4s2. And so for the ion, it's 3d7. Yes?
So if it was 3 minus, then
Yeah, if this was a 3 minus ion, we would add 3 electrons and then they would be paired up. Let's do nitrogen. So, well, is there really any point in doing the noble gas since helium, right? We'll just draw the box. There's 1s and 2s and 2p. And the atom has how many electrons? 7. 1, 2, 3, 4, 5, 6, 7. And so the electron configuration for the atom would be 1s2, 2s2, 2p3. But it's a 3 minus. 3 minus sometimes makes us want to subtract 3. It's a 3 minus charge, and that means it's got 3 extra negative charges, so we have to add 3 electrons. So I'm going to add 3 electrons. They're going to go here. I made them slightly darker. I don't know if you can tell that or not. Doesn't really matter. So now I've made the ion, and then I have to change this because now it's 2p6. Yes? This is diamagnetic, yep. Diamagnetic because di means 2, 2 by 2, all the electrons paired up. Paramagnetic is the other. It's not spelled the same as pair. It doesn't mean pair, it means something else. Any questions? So again, we're talking about ions here. We're going to look at trends in ionic radius. So to make a cation, you take electrons off. So is that going to make the atom larger or smaller? It's not a trick question. It's going to make it smaller, right? You take stuff off, it gets smaller. What is surprising is how much smaller the cation is. And here, just, for reference, we have, here's the lithium atom has a radius of 152. The lithium ion has a radius of 60. It's less than half the size by removing one stinking electron. So there's two things happening here. You're removing the outermost electrons, those valence electrons, so that's peeling off a layer of the onion, right? But then you also have an increased nuclear charge, effective nuclear charge, for the remaining electrons. Because what used to be core electrons are now valence electrons, and so there are fewer core electrons, and the charge, effective charge, goes way up. And so you'll lose an electron or two, and the rest of them really get sucked in. They get a lot smaller. So what I expect you to remember from this is cations are much smaller than neutral atoms. Anions are much larger than neutral atoms. That's kind of nice and symmetrical. And again here, the difference can be like twice as much. So here's fluorine goes from 72 to 136 by adding one electron. That's almost doubling in size, doubling in radius, right? Crazy. What's going on? Well, we're adding electrons with no change in the nucleus. And so even though we're not adding core electrons, the effective nuclear charge is getting lowered. What I told you, Z minus S, that's an approximation of the effective nuclear charge because the valence electrons do repel each other a little bit as well. So at this level, I can't give you a great explanation of why, but anions are a lot bigger. Any questions? Isoelectronic ions. This prefix iso means the same. So, same electron ions. These are ions that have the same number of electrons, even though they're different elements. And so that can happen with several different combinations. So here, the sulfur 2- ion. Sulfur has 16 protons. The atom has 16 electrons, but 2- charge, we've got 18 electrons. Chlorine has 17 protons, 17 electrons, but you get a -1 charge, 18 electrons. Same number of electrons. Here's potassium and calcium. They also have 18 electrons. What's the element, the atom that has 18 electrons? Argon. All of these have 18 electrons because they are gaining or losing electrons so that they have the same number as argon. Yes? P there is for picometers. So, yeah. So this is the radius. So sulfur, the sulfide ion, 184 picometers, 181 picometers, 133, 99. So they all have the same number of electrons, but their sizes are different because the charge on the nucleus is different, right? Calcium has 20 protons, sulfur has 16 protons. More protons, more charge, pulling the electrons in. Okay, choose the larger atom or ion from each pair. So, potassium the atom or potassium the ion? It's like, well, when it becomes a plus ion, does it lose electrons or gain electrons? It lost an electron, so that should make it smaller. So then the larger one is the potassium atom, right? Fluorine or fluoride? Well, when it goes from fluorine to fluoride, are we gaining or losing electrons? Gaining. We're adding stuff to the outside. That makes it bigger. So fluoride is bigger. Those should be pretty easy, unless you trick yourself, right? Sometimes it is as simple as it seems. So then calcium or chloride. So here we need to think a little bit more. You're right, the answer is chloride. So these are isoelectronic. The number of electrons, this one has 18 electrons. This one also has 18 electrons. But this has 17 protons, and this has 20 protons. So same number of electrons in the same configuration, but larger charge on the nucleus. I would expect this to be smaller, so the chloride is larger. Adding electrons makes it bigger, right? Anions are bigger than the neutral atom. The neutral atom is bigger than the cation. So in an isoelectronic series, you can also just look at who's the most negative. That one's going to be the biggest. And the most positive will be the smallest. So ionization energy. We kind of came across this in worksheet 8, where you had to calculate the, I think it was the wavelength of light needed to ionize a hydrogen atom. So ionization energy is the energy needed to remove an electron from an atom. Ionization energy is always positive. It always requires that you put energy into this to remove the electron. There's a cost, right? So positive ionization energy, I am the atom, and I'm going to be losing an electron. I'm not going to pay you to take my electron. You have to pay me. You have to put energy into me, positive for me, to take my electron, okay? Unlike some days, as a stay-at-home mom with 6 children, when if the circus had come by, I probably would have paid them to take a couple, but thankfully they never did. Yeah, anybody. So it's always positive. So we can write a general equation, and this is a technicality, but it's always in the gas state, because if you were to do it in from the solid or liquid or something, it would be different. But here we have the element, and we're just using M as a generic. M in the gas state plus ionization energy 1 will give us a positive 1 ion plus an electron. So this electron is now separate from the atom. This is called the first ionization energy. It's to remove the first electron from a neutral atom. Yeah, those are the balances doing their little calibration thing, and they sound like sad cows. Meow. It's really disturbing during an exam when they just start mooing at you. Yeah.
So, you're removing an electron.
Mm-hmm.
So it's becoming positive, but you just separate. So that's the one
Yeah, so this is the electron that is getting removed. So they were all together to start with, and now we have the cation and the electron, and they're separate. Yes.
When you do the second one below N2+, would it be 2 electrons taken out?
That's a good question. So the second ionization energy is when you're starting with an ion that already has lost 1 electron. Because we're not looking at the energy to remove 2 electrons at the same time. We're going to take them off one at a time. The first one comes off, now we have a +1 ion, and if I take another one off, I'm going to go from +1 to +2. And so that's usually signified as IE2, the second ionization energy. We're removing it from a +1 ion. Yeah.
If we're writing this on an example for your response, would you leave the one electron just like in the equation? So knowing the last time we ended up like crossing them out, and we just leave them.
Yeah, you would leave this here because unlike when we were balancing the redox reactions, the reason we crossed them out is we took one like this and we added it to an equation that had electrons as a reactant. So then we had reactant and product, and that's why they crossed out. Any other comments, questions? Whoops. So there are trends in the first ionization energy. As you go down a group, the first ionization energy increases. So for the noble gases, helium has the highest first ionization energy of those, and as you go down the group, the energy required to remove an electron becomes smaller. Because the atom is getting bigger. So the electron, you're going to be pulling off a valence electron because those are on the outside. The electron is farther from the nucleus, and so, if we're thinking about Coulomb's law, the energy is proportional to Q1, Q2 divided by the radius. So in a larger atom, the radius is bigger, the electron's further away, it's easier to pull it off. Small atom, closer, harder to pull it off. And this always makes me think of the big Fresno Fair and why I never took my children there after I got more than a couple children, because so here helium has 2 electrons, right? So this is a mom going to the fair. She's got 2 children. She's got 2 hands. She can hold on to both of them, right? Kind of hard to take one of those kids, because that's what an ionization energy would be, is like snatching a child. Not politically correct. And I'm not, yeah. Just for us to remember what's going on here. So here we've got more children, and so here's xenon with a bunch of children. So even if they're all, like paying attention to you, they're still going to be further away as you're walking around, right? You don't actually have a grip on them. And so here I am at the fair with 6 kids, and my friend has 2. If you're going to try to snatch a kid, you're going to pick one of mine, right? Because I don't have physical hold on them. It's easier. So larger atom, easier to pull an electron off of. What about going across? Well, again, it relates to the size. So as we go across a period, are the atoms getting bigger or smaller? They're getting smaller. Smaller atom, electrons closer, harder to remove. So as we go across a period from lithium to neon, from sodium to argon, it becomes harder. The ionization energy increases. It's not linear at all. It's kind of jagged, but it increases. And that is really due to the effective nuclear charge, which is the reason why the size is different. Another way to think about that trend is, so I'm looking at each end of this period. Next to neon, we have fluorine, right? So does lithium form positive ions? It's in group 1, it forms +1 ions. It does that by losing an electron, right? So it must be fairly easy to remove that electron. Does fluorine form a +1 ion? No, it forms a -1 ion. So it's really not going to like having an electron removed because it's trying to get an electron. So it's harder for fluorine to have an electron removed, if that helps. Bless you in the next room. So here's what kind of a chart is this? I don't know. It's the pillars, right? It looks like pillars to me. And how tall the pillars are is 3-dimensional. It's kind of cool. So here we see the ionization energy as the height of these columns, and so here it drops dramatically as we go down here. We can see in all of these we're dropping as we go down the period, and as we go across, in general, it's getting larger. Okay. On the basis of periodic trends, determine the element in each pair with the higher first ionization energy if possible. And so this is like when we were doing the sizes, right? We've got a trend going across, we've got a trend going down. Sometimes they correspond with each other, sometimes they conflict with each other. So tin or iodine, that's that same pair we did earlier. So there's tin and there's iodine. And rather than just trying to memorize this stuff, I think it's best if you can reason it out. We spent kind of a long time talking about the size of the radius, because if we can think about that and have that trend firm in our minds, then that's going to help us decide what these other trends are going to do. So going across, which one of these is bigger? The tin is bigger. So this one's big and this one's small. And so what I'm looking for is the higher first ionization energy. Is it harder to pull an electron off of a tiny atom or a big floppy atom?
Is it harder?
Harder. It's harder to pull off the smaller one. You know, that's the mom with 2 kids. She's got a grip on each of them, right? And then there's me, and I can only hold on to 2 at a time, and not even that. So who's got the higher ionization energy? Iodine. Calcium or strontium? So this is over on the left side. There's calcium, and well, I drew an extra one, but there's strontium. So first identify which one's bigger, which one's smaller. Strontium's bigger, calcium's smaller. So we're looking for the higher first ionization energy. Which one is it going to be harder to take an electron from? The smaller one, the calcium. Carbon or phosphorus. Here's carbon, here's phosphorus. Well, let's first think about bigger and smaller. Well, going across predicts that phosphorus is smaller, that trend, but the up and down trend predicts that phosphorus is larger. So we have opposing trends, and that's why it says if possible. So we're just going to say not possible. And then we've got fluorine or sulfur. Here's fluorine, here's sulfur. Again, a diagonal, but the trend going across tells me that fluorine is smaller and that sulfur is bigger, and the trend going down tells me the same thing, that fluorine is smaller, sulfur is bigger. So fluorine's definitely smaller than sulfur, so then fluorine has the higher ionization energy. Any questions? Exceptions. Of course there have to be exceptions. First ionization energy generally increases from left to right, but we have an exception between group 2A and 3A. Well, we see it best in this graph. So there's group 2A and group 3A. Group 2A and 3A. So we see this jump here. Here's group 2A and group 3A. 2A and 3A. So we expect it to get bigger, and it actually got smaller. So there's actually a reason for that. So draw orbital diagrams for boron and beryllium. And we're just going to do the valence electrons. So for boron, the helium, and then there's 2s and 2p, and boron has 3 electrons over here, right? 1, 2, 3. And then we'll look at beryllium. I'm just going to draw the same boxes even though I don't actually need them. And beryllium just has 2 electrons there. Okay with that? So the first ionization energy for these, I'm taking out an electron. So for beryllium, I'm going to take that electron out. And for boron, I'm going to take this electron out. Beryllium is losing an S electron. Boron is losing a P electron. Which of those is higher in energy? Which one fills last? The P. The P or subshell fills last because it's got higher energy. So it's easier to remove. It's easier to remove than this S orbital. Because we're removing from different orbitals, on different sublevels. We see another exception between group 5A and 6A. Slightly different reason. So here's nitrogen. Nitrogen has a nice orbital diagram here because this P sublevel is exactly half full. And so there's a little bit of a bonus there, a slight lowering of energy. And then here's oxygen. And oxygen, we're going to remove an electron, we're going to take this electron, and that will give us a half filled, which is kind of nice. There's a bonus there. When I take an electron from nitrogen, I'm messing up the half-filled room. So that's one way to think of it. This electron is having to pair up. It's not as happy about it, and so this one's easier to remove than we would predict. These exceptions are not a big deal. I have to tell you about them. So trends in successive ionization energies, this is where you're looking at the same element and you're going to remove one electron and then a second and a third and a fourth and a fifth. So here's sodium over here. And the first electron costs 496 kilojoules to remove. So that's not so high. The second one is huge. It's almost 10 times as big. 4,560, and then this one is 6,910. We expect that it would get bigger as you're pulling electrons off, but we don't necessarily expect this huge jump. If we look at magnesium right next door, removing one is 738, and that's what we see that trend as it gets larger as we go across the period. But the second one is only like twice as much. So it's just kind of the same sort of a jump, 1450, and then the third one is huge. So what's going on there? Well, here for the first one, I'm losing a valence electron. The second electron for sodium that I remove will be a core electron. Those are much closer to the nucleus, and so it's going to be a lot harder to remove those. For magnesium had 2 valence electrons. The first one came off pretty easy. The second one's a little bit harder. But now that I've got all those valence electrons, the first core electron is a huge increase. Here, what this chart is showing us is the elements in period 3 going across, and their first ionization energy. And the pink here is where you're removing the first core electron, and that's where this big jump comes. So for aluminum has 3 valence electrons. You remove those, and then there's this huge jump with the first core electron. Silicon has 4 valence electrons. So there's the 4 valence electrons. And again, huge jump for this one. And so we see that for all of these. But argon is just, well, we're not getting into the core electrons of argon.